Hey everyone, I'm glad that you are watching this because that means that you are as interested in Bayesian time to event analysis as I am, or at least I hope that's why you're watching this. My name is John, and this is the first in a set of videos that are designed to help you get an understanding of what Bayesian time to event analysis is. So, before we can jump into any of the fun stuff, first I'm going to explain just what time to event analysis is and some basic principles and concepts that are going to be needed. So, a few examples of time to event data include the time to death after being diagnosed with leukemia, which we're going to look at later on, the time it takes to get sick after infection with a virus, and the time it takes for a light bulb to go out. As you can see, whether we are looking at the time until death or the longevity of a product, time to event analysis is extremely useful. Now, let's look about how to distinguish time to event data. There are two features in particular that define time to event data. The first is that they are positive, and the second, they are often censored. Now, censoring is a term used to describe partially observed data, and I'm going to talk about that in a little bit. But as far as being positive goes, it makes sense when you think about how time to event data mainly concerns measurement data, and most measurement data are going to be positive. So clearly, time to event analysis serves a very important role in society. You see, a type of time to event data known as survival data is what is used in assessing many problems in the medical industry. That is why type to event analysis is more concerned with relative probabilities than things like means and variances. So, for example, with two competing cancer treatments, a time to event analysis is much more likely to care about the relative probabilities of surviving past 5 years for each group. Now that we know about the data type, let's look at the techniques that are going to be used. Time to event analysis employs different techniques compared to other statistical analysis. First, know that time to event data often depend on covariates. So, risk factor information such as race, gender, age, etc., at the beginning of the study or treatment regimen are often associated with survival outcomes. So, in other words, there are many factors that could affect what we were analyzing, and we have to take them into account. The second change between other types of analysis and time to event analysis is the inclusion of censoring. So, now let's talk about censoring. Okay, imagine you are conducting a study to see if a new treatment for, I don't know, colon cancer is effective. So, as a scientist, because you are limited in your funding, let's say the study lasts 10 years. In those 10 years, subjects will die as a result from colon cancer. However, it is highly unlikely that everyone in the study will die within those 10 years. It's just not plausible. Conversely, you might see a subject die in a car accident, which clearly has nothing to do with colon cancer. The question now is, what do we do with those subjects? And the answer, of course, is censored. So for a formal definition, let C be a random variable that denotes the time at which a censoring mechanism kicks in. What we actually observe is either the event T or the censoring time C, whichever is smaller. The observed data are Y equals the min of T and C. We also have to include an indicator random variable for the non-censoring observations, which we're going to call delta. So delta is going to equal 1 if T is less than or equal to C, and 0 if T is greater than C. There's also a few censoring assumptions I need to mention. First, T and C are going to have to be independent. We can't have someone both alive and dead. That is, unless your subject is Schrodinger's cat. We also assume something called non-informative censoring. This means that the censoring distribution does not depend on any of the same parameters. Finally, most experiments follow right censoring. So let me give you guys an easily understandable scenario that's going to depict what right censoring is. Suppose patients are followed in a study for 10 weeks. A patient who does not experience the event of interest for the duration of the study is said to be right censored. Basically, right censoring is just censoring that takes place at the end of the study rather than in the beginning or the middle. Now, since this is an introductory video, I might as well review a few basic distribution functions while I'm here. So first, we have the cumulative distribution function, or the CDF. The CDF can be thought of as the probability that a random variable, say t, takes a value less than or equal to some value, say little t. I don't know why we have to do big T's and little t's, and anyways, when we are dealing with continuous distribution, the CDF gives the area under the probability density function from minus infinity to little t. Some features of the CDF include it being equal to 0 at t equals 0 and approaches 1 as t increases. It is a non-decreasing function. Now we have the survival function. The survival function is pretty much just the opposite of the CDF. So that means that it gives the probability that some object of interest will survive beyond any given specified time. It is also known as the reliability function. Some characteristics of the survival function include it being equal to 1 at t equals 0, and it approaches 0 as t increases. It is a non-increasing function. So the characteristics are going to be easy to remember since, like I mentioned before, they're just the opposite of the CDF characteristics. A distribution function that you guys might not be too familiar with is the hazard function. So to talk about the hazard function, I need to bring up the failure rate. And the failure rate is the frequency with which a component fails, expressed in failures per unit time. It is important to note that the failure rate of a system is usually dependent on time. This is because if we calculate the failure rate for a really small interval of time, we end up with what is known as a hazard function, or hazard rate. In other words, the hazard function is the instantaneous failure rate as the change in time goes to 0. The slide here shows the full mathematical definition if you're into that kind of stuff. And that pretty much covers what you need to know about the background of time-to-event analysis. Next time, we're going to review a few distributions that will be needed for further use, like the exponential and gamma distributions. Also, because time-to-event data behaves so differently compared to other data types, we need to go over the likelihood function. Trust me, once we get through the reviews and basic principle stuff, we're going to start getting some hands-on experience using real data, and that's where the fun stuff comes in. Anyway, I hope you enjoyed this video, or at least learned something from it, so see you guys later.